Okay, we're going to try something new with the AP Chem stuff. So on the board here we have 2019A, and I suppose I should probably label B. Okay, in question A, it's asking for the hybridization of the carbon atom. So we can ignore literally everything else. We can ignore everything else, and all we care about is the carbon. Hybridization refers to how many different elements or different atoms, more accurately, this carbon is attached to. So let's just go count. It has 1, 2, 3 different molecules it's attached to. Now, if you go way, way back to the lavender sheet, or think back, hybridization always is based on the number of things you're attached to. It has 4 bonds, but only has 3 ligands, or 3 different things it's attached to. So the way we count this is we go S, 1, P, 1, 2. So this would be SP2 hybridized. And this is how any hybridization works. We go S, SP, SP2, SP3, D, SP3, D2, SP3. Let's write that out. Your hybridization options, you'll always have at least SP, or actually, you'll have S, SP, SP2, SP3, SP3, the D out front, D2, SP3. This is attached to 1, 2, 3, 4, 5, and 6 objects respectively. Okay. This is a factual-based question. We're probably not going to see a whole lot of these on the AP exam, but the understanding of what's going on here does carry on to other information. Once again, your answer here is SP2. The next question. Urea has a high solubility in water due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw 1 dashed line, ... to indicate a possible location of a hydrogen bond between water molecule and the urea molecule. So, the scoring guideline has an answer. Let's do this in red. Here. There are several other possible answers. Here. Let's talk about what the scoring guidelines say and how it got there and how I would attach this problem. A dash line should connect a hydrogen atom in water to a nitrogen, or an oxygen atom in urea to an oxygen, or an oxygen atom in water to a hydrogen atom in urea. One possible correct response is shown above. So another possible response here would be here and here. And when I think about this problem, the first place I actually go is back to this Lewis structure over here. So let's go ahead and draw water in right here. We're going to draw 2 waters. We're going to draw one like this. We're going to draw another one like this. Okay. Hydrogen bonding is built around the idea that when you have a very electronegative element, like oxygen or hydrogen, the electrons in the bond are going to tend towards the more electronegative element. And if you think back, you remember these arrows that we would draw like so. Okay. Now, hydrogen bonding is exceptionally strong because hydrogen is effectively just a proton with an electron. And if you pull that electron away from it, you pull it away. It's just a free-hanging proton, very positive, which would then, or can then, be attracted to these very negative sections on the nitrogen or the oxygen formed from those lone pair electrons. And like everything, tying back to Coulomb's law, it's always a positive to negative attraction. The arrows here point to a negative region, and the plus signs at the bottom indicate a positive region, which tells us that if we're going to have a positive to negative, it would have to come from the hydrogen to the lone pairs here. It could be really from either one of these. One of these would be a good option, or it would have to be from the positive hydrogen to the negative oxygen. Again, here or here. Any one of these possible drawings in orange over here or red over here would be an acceptable answer to B. Okay, the question then goes on to C. C asks, or states first, the dissolution of urea is represented by the equation. It says above, but we're going to put it below. Let's go ahead and write this equation in. H2NCO NH2 solid goes to H2NCO NH2 aqueous. Okay. A student determines that 5.39 grams, number, stop there, underline it, it's probably going to be important soon, of H2NCONH2, or urea, with a molar mass, probably important, of 60.06 grams per mole, can dissolve in water to make 5 milliliters of a saturated solution at 20 degrees Celsius. Okay? Calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees Celsius. Awesome. So, this is asking you to calculate something. It's looking for a number. So I need a number to represent moles per liter. What's the molarity? So I want something in moles per liter when I'm done. Well, I don't have moles in liters. I have milliliters. That's probably going to be useful. But I don't have moles. So, stuck on this problem, thinking about it for a second. Where do I go? What do I do? Well, I look at my numbers. I go, okay, well, I have grams per mole. That means if I have grams, I can get 2 moles. Well, then I have grams here. So on top where it says moles, because I can get from grams to moles using this number here, I do 5.39 grams goes on top. And strictly speaking, this should be labeled urea. If you don't, that's okay. I'm not always the greatest. Per liter. Well, liter is a volume. The only other volume I have here is this 5.0. I guess I'm probably going to be using that. Okay, I'm in grams per milliliter right now. I need to get to moles per liter. So let's convert. I'm going to do the milliliters first because it's the one that we always know. It tells us that 1,000 milliliters is 1 liter. Milliliters cancel out. I'm losing with liters. Okay, I got one of my 2 goals. Second, 5.39 grams. Well, it tells me here that 60.06 grams is 1 mole. So instead of saying 60.06 grams up here, which would give me double grams, I'm going to do 60.06 grams is 1 mole. And that's the molar mass. Notice how it gave that to you. You didn't have to look it up. You didn't have to do anything. It gave you that number. Saves you a little bit of work. Okay? The grams. Urea cancels with the grams. Urea. Leaving with moles. Urea. Per liter solution. But wait, we didn't use the 20 degrees. Well, temperature does affect concentration. We know that. But in this particular problem, it's 20 degrees, 20 degrees. The temperature doesn't change. All this is saying is the number we find is only valid for 20 degrees. It's superfluous. It's extra information. It doesn't tell us anything about concentration. We don't have any equations to tie them together. So don't worry about it. Throw it out. If I do all these numbers correct all the way through, I should get 17.9 molar, or capital M. You could also say 17.9 moles per liter, which is what they actually asked for right here, but these are analogous. Why 17.9? Well, let's talk sig figs. On the 5.39, there are 1, 2, 3 sig figs. On the 5.00, there are 1, 2, 3 sig figs. On the molar mass, it's a given quantity. It's assumed to be infinite, but even if it wasn't, there are 1, 2, 3, 4 sig figs. When you do sig figs, you always take the lowest number when you're multiplying. 3, 3, and 4. Out of those, 3 is the lowest. So 1, 2, 3 sig figs. Okay, question D. The student also determines the concentration of urea in a saturated solution is 25 point at 20 in a saturated solution at 25 degrees Celsius is 19.8 molar. Based on this information, is the solution of urea endo or exothermic? Justify your answer in terms of Le Chatelier. So, first things first, we need our answer from C to talk about this. Okay, now the temperature's changed. We've gone from 20 to 25 degrees. Two things. Number one, the main way I know that this and this question are tied together is because, one, there's the change in temperature, and two, the header text here hasn't split these two questions up. They're next to each other in terms of the header text. The next question is broken up by this picture here, setting these two apart. So I know that these are together because this is much like here, these two are next to each other because they're related. You need the hybridization and this Lewis structure to talk about this. These are together because there's this header text between them that ties them together. So, going back to this. 19.8. Well, on the last problem, we calculated 17.4. So we have more at 25 degrees Celsius than we do at 20. More. So at higher temperatures, I have more dissolved. So, with that in mind, let's go through this. So if we have more dissolved, we got to go back to the equation. We're talking about Le Chatelier. Le Chatelier is a big hint that we need to look at the equation. So here is our equation. Now, we have more dissolved. So we have more on which side of the reaction? Do we have more solid or more aqueous? Well, aqueous means dissolved. It's broken up into solution. And we have more over here. So if we have more products, we had to have added a reactant between the two reactions. Adding more reactants shifts the reaction towards the products. Okay, so by adding heat, we have shifted the reaction to the right. So adding a reactant, adding heat, has transitioned this to the right. If heat is a reactant, then it has to be, by definition, endothermic. Justification in terms of Le Chatelier. By increasing the temperature, we have gone from a lower concentration to a higher concentration of urea dissolved. based on Le Chatelier, this increase in products indicates that there was a addition of reactants. Since the increase of temperature is treated as a reactant, the reaction is endothermic. Done. Check the scoring guidelines. They give a little more description, but that's how I get there. That's my logic. E, the equipment shown above is provided so the student can determine the value of the molar heat of the solution of urea. Molar heat. They want you to do calorimetry. That's what all they're asking. What do you need to do calorimetry? Knowing the specific heat of the solution is 4.18, close to water. They're just going to tell you to use water most of the time. Joules per gram per degree Celsius. List the specific measurements that are required to be made during the experiment. Okay, so what do we need to do calorimetry? If you don't remember, go look at your notes. But absolutely, I would prefer to use 2 cups, but 1 will do. To keep the do the reaction in, I need something to cover it. Awesome. But it's not asking about. But notice how I just fell into a trap. It didn't ask anything about the requirements. It says list the specific measurements. Okay? Measurements. I don't care about this material. This material is useless. Doesn't tell me anything. Not even part of the question. I'd like to give you this junk information to throw you off. So, throw that aside. Throw it out. We don't care. Let's go ahead and tackle the problem. What measurements do we need? Well, if we go back, we need to know how much the temperature of the water rose to get the delta H reaction. We needed to know how much urea we added so we can get the number of moles. We need to know how much water was in the cup. And we need to know initial, final temperature, mass of urea, mass of water. I think that's it. Let's double check because I'm not sure. And the scoring guidelines agree with me. Okay. Do be careful with this one. This is tricky. It's asking for measurements, not tools. You don't care. This right here is superfluous.